Right? In this case, we need spokes and a rim. How many spokes do I need? 32. I can count fast. I'm making that up, actually. I don't know. I think it's 32. Okay, what else do we need? We probably need the rim. How many rims do we need? One. That's a lot of words to write. I wonder if I could abbreviate that. I need 32 spokes, and I need one rim. What have I just built? A chemical formula. Okay? Using things we've already dealt with. That's what chemistry went through and did. It takes too long for me to write all those pieces down, so I'm going to come up with a shorthand. Instead of it being spokes, I'm going to write SP. Okay? Instead of writing 32 and rim, I want to combine those pieces. We could have just as easily said, well, it's one wheel and create a new symbol. But the problem with that is then I have to use a new symbol to represent every single thing on the planet. Which means how many symbols do I get? How many different things are on the planet? A lot. We're probably pushing into an infinite amount of things. Okay, which would mean an infinite amount of symbols, which would mean we all have to learn an infinite amount of symbols. That's not going to work out well for us. Okay? So what chemistry went through and did is said, well, those smallest component parts, I'm going to symbolize those. And now what I'll do is when I take those component parts and build larger things, I'm just going to say that larger thing is made up of those component parts. That's how we got to chemical formulas. Okay? The meaning behind all of that goes back into how we would build those things out. Kind of, sort of? Okay. So how do we use that for a chemical formula, like sodium carbonate? Well, what is the formula for sodium carbonate? So what is sodium? Na. What is carbonate? CO3. Is this the proper formula for sodium carbonate? So if I now ask you to build the wheel of sodium carbonate, what are the component pieces that would need to go into it? Well, we'd look at the wheel, the formula, sodium carbonate, and I'd say, well, one sodium, right? And all of a sudden, miraculously, we'd be wrong. Well, why?
Because of the charge on carbonate.
Is this a valid formula for a wheel? SPR. No. Why not?
So it's not 32.
I needed 32 spokes to make that. I had to include the 32. Why did I know that? Well, I could deal with the wheel. I can physically see it and see how many pieces it needs to go into it. Chemistry becomes difficult because we can't physically see it. Right? So we have to make parallels back to the connections that those things would make and kind of predict those outwards. Right? Those connections we can discover by looking at their charges. What was the charge on a sodium ion? A +1. A charge on a carbonate? -2. Those connections aren't balanced. What I've written there is SPR. That doesn't allow me to build a wheel. For that same reason, that doesn't allow me to build sodium carbonate. So I can't interpret that formula yet. I need to make sure that formula is correct to interpret it. How do I fix it? I need 2 sodiums. Now my formula is correct. Now I can interpret how many sodium pieces went into sodium carbonate. Okay? This is why we have to understand nomenclature and how those pieces come together to create that larger formula. Okay? So the formula allows us to see those relationships of those component pieces and come up with relationships between them. Those relationships are said another way. They're conversion factors. When I look at the relationship between milligrams and grams, well, 1 milligram is 10 to the -3 grams. That is a relationship. I can use that relationship to do what? Convert. This chemical formula allows me to interpret out and pull out relationships of the parts to the whole, or the parts to other parts. Each of those relationships is a conversion factor that allows me to now convert parts to wholes or parts to parts within the whole system. Okay? What makes it extra difficult in chemistry is we can't see those pieces to be able to grab a hold of them to see those connections. We have to just kind of imagine them. So if you can imagine each chemical formula you see as something else, like say a bicycle, that can help you process through some of what those things mean and how to interpret them. Okay? And that's why you'll see chemists talk a lot about these larger objects. When we talk about a mole in the video, we talk about how many, I don't think I used the example in the video, how many donuts it takes. If we had a mole of donuts, what would we be able to do with it? How much space would that take up? Okay, there's a different video that had that one that I was going to do, but I didn't like it. Okay, in the video I talk about how much money would you have to spend, okay, every hour for every person on the planet. How much money would you have to spend?
A mole.
Okay, to spend a mole of pennies. Well, pennies are insanely tiny, so right, it can't be that much. Right? $14 million. Every person on the planet, if we assume every person lives for 100 years, to spend a mole of pennies, okay, in that time span, every person has to spend $14 million every hour. No sleep. That's a lot of freaking pennies. We took something that had virtually no value and turned it into something that has an insane amount of value for our brains, because probably none of us are going to see $14 million ever in our life. Okay? And we're now saying to get that mole of pennies, we have to have that every hour. Okay? What we're trying to do is scale something that is so astronomically large into something that's a little bit easier for our brains to comprehend. And even 14 million, we can't comprehend because we'll never see that in our lifetime. If you add up all the money you ever consumed through your entire lifespan, it's probably not even going to hit 14 million. And to achieve a mole of pennies, every person has to be spending that amount per hour. That's insane.
Including your 2-year-old.
Okay, including my 2-year-old. Okay, that's nuts. Okay? So what we're trying to do is pick examples that allow us to take these really weird, large or small numbers and scale them into systems that allow us to work. Okay? The really simple example that is used in the video, okay? We've done this before, and people complain about moles and bring, well, moles is stupid. Why do we need to invent this new unit? Okay? I can deal with that number. Humans are so horrible at dealing with large numbers, okay? The capacity for the human brain, the largest number we can deal with, 10. Like, I can count to 12. Probably, okay? But your brain doesn't do a good job of it, and that's because our direct evidence to prove that statement, what happens when we reach 12? We ran out of fingers. So what did we do?
I thought we ran out when we went to 10.
Fair enough. What do?
We moved to toes.
Instead of it being single digits, we now said when we hit 12, it became a dozen. I don't go to the store to buy 12 eggs. I go to the store to buy a dozen eggs. Our brain is so freaking horrible that I can't say I'm going to the store to buy 12 eggs. I have to go to the store to buy a dozen eggs. Okay? So for those who say my brain's that good, if I ask you to go to the store and buy eggs, you're going to immediately say you're buying a dozen eggs. Your brain isn't that good. Yes?
Programs to think that way? Or is it just
So,
our brain?
if we look at our context, we're probably now programmed to do it. But why was it created to begin with? Because they couldn't do it. Right? So a lot of our actions that we're running on are historical.
So they
right?
used all.
So they used all.
Okay.
Yes.
Couldn't we technically argue that you can go to 13 because you have a baker's dozen?
That's doing a different marketing system, not a numerical system. You could also make the argument that you should be able to count to at least 12. Why? And I would argue, why is 12 now the number that you could count to? I just thought of this. Because shouldn't you be able to count to 20? We got 5 fingers on each hand and 5 toes, right? So I should be able to count to 20. Why can't I count to 20? I just covered all of those numbers with a shoe. I can't count beyond 12 because there's 5 fingers on each hand. There's my 10, and I'm not lifting my foot up that high again. 1, 2 for my extremities. I can get to 12. How do I get to 13? Crap, I'm out of extremities now. Okay? Dozen. Now I can count 1 dozen, 2 dozen, 3 dozen. Okay? I'm hoping you didn't make reference to what I thought you did, so we're just gonna.
About counting systems on our fingers going from 12 here and up to I think it was 72 if we use each set for 12 sets of 12. Yeah.
So we can
cover that with writing systems.
We can come up with other ways to approach those numbers and scale, okay? But that also requires a higher technological advancement, okay? Which requires more thought. The more thought, my 2-year-old might be able to get up to 12, but he's going to have a hard time going after that. Okay? Even if I go through, well, you can also count these as 12. Yeah, he's still going to have a hard time with that. Okay? So at the simplest level, we really can't deal with that. We can invent systems to help us deal with larger numbers, with counting with our fingers and hands. We can also invent new units, moles in a dozen. Ta-da, they're the same thing, just using different aspects of language, ultimately, to represent them. Okay? The equation does the same thing. When we look at a chemical equation, it's allowing me to relate different substances. Just like when I looked at a formula for sodium carbonate, it allowed me to relate the sodium to the carbonate, the sodium to sodium carbonate, the sodium to carbon, the sodium to oxygen, okay? Because the chemical formula showed me those relationships. Well, a chemical equation does the exact same thing, but now at a grander scale, because I can convert molecules to other molecules. Right? Why is that going to be more important for us? If we went out in the world and tried to find sodium, where do we find it?
Can you repeat the question?
If I go out in the world to find sodium, where do we find it? And an awesome suggestion, I love it, salt. Did you find sodium?
No, we don't.
You found salt, which was sodium chloride. You didn't find sodium, you found a compound. Okay? Sodium is not readily available in the world. Why? It is highly reactive as the metal, and it reacts with the outside environment to make a compound. So looking at an individual formula and saying, well, sodium chloride, I can get sodium and chlorine, neither of those substances are readily available in the world. I would have to find them from other compounds. Well, how would I get them to then form? I would have to do a chemical equation. The chemical equation now allows me to convert those things more appropriately because I can't find these things as their elemental state, right? In a large number of cases, at least the useful cases. Okay? Yeah, we're going to skip that. Okay? We'll come back to it in a little bit. So Avogadro's number is now a scaling system. That's the reason we invented it. Okay, so when we talk about a dozen, the word a dozen, okay, means 12. Okay? 1 dozen equals 12. And really what it equals is actually 1 times 12, because dozen means 12. Okay? If I asked you to go to the store and buy a dozen, what are you going to come back with?
Well,
A dozen what? I didn't tell you. Right? The mole and a dozen are just a scaling factor. Okay? So it is actually incorrect to say a mole is 6.022 times 10 to the 23rd atoms. That is technically wrong. Just like it is technically wrong to say 1 dozen is 12 eggs. No, it's not. Because if I ask you to go to the donut shop and buy a dozen, are you going to come back with eggs? No, you're going to come back with donuts.
And I ain't coming back with a dozen.
So when When we think about a mole, what the mole is a dozen. It's that scaling factor. Okay? A dozen is a scaling factor. I'm multiplying up by 12. What is a mole? A mole is a scaling factor that scales the number of that object, the substance, up. Okay? Would it make sense to say, go buy a dozen grams?
No.
No. Why is that now a weird statement? Whatever relate a dozen grams to mass.
Because you made it a weird statement.
No, because a grams of what, and then grams are such a small.
Alice said something.
Different idea. What do you got?
Say 12 grams.
I would say 12 grams. I wouldn't say a dozen grams.
Oh.
Okay, well, why? What is a dozen measuring?
12.
12 what?
Anything.
Not quite anything.
12 things.
12 things. What is grams? Grams is not a thing. Grams is a measurement. Okay? So we can't relate grams into this. If I ask you a dozen grams, okay, you're not telling me the measurement 12 grams. You're telling me that you have 12 objects that all weigh 1 gram. Okay? That has an entirely different meaning behind it. We're not relating mass to the number of things. We're saying there's this number of things. Each of those things happens to weigh a gram. Okay? So when we're looking at a mole, and for that matter a dozen, we have to be very careful that the measurement unit we're using, okay, isn't strictly a measurement. It's a physical object. It is things, not a measurement. What are our things in chemistry? That wasn't a rhetorical question, just in case you were curious.
It could be.
Could be is a good start to that.
Could be elements, could be, or like atoms.
Atoms would be a phenomenal thing, right? That's why we started with atomic theory. Okay, what was the smallest unit in chemistry? It was our atoms. We then said that those weren't the smallest things, that they could be broken down. But when we go through to build water, do you tell me about the protons, electrons, and neutrons?
No.
No, what do you tell me about?
The elements.
The elements, the atoms that made it up. So the thing in chemistry, atoms. Is that all I talk about? It's just atoms.
No.
No. What is water? Is water an atom?
No.
We could call it a compound, right? Which is a fair term to use. I have no idea why I've never used it, but as a rhetorical choice, compound is actually a much better choice than the word that I was thinking of. What's the word that I'm thinking of?
Equation.
No, think back to compounds. So compounds is a phenomenal word choice. That's actually much better than I've ever used before. I don't know why I never thought of it. Because I'm an idiot. That's fine.
Molecule.
Molecules. Compounds and molecules are ultimately the same thing. Trust me, that says molecule. Okay? Why is compounds a better word than molecules?
Because compounds can be a combination, whereas molecules can be just.
Are molecules not a combination of atoms?
Can't you have just a molecule of hydrogen? Wouldn't that be separate from?
So, yes. Okay, so let's look at that, because that's going to be relevant for the question that's actually underneath. Can I have a molecule of hydrogen? Yes. What is my symbol for that?
H.
Is that a molecule of hydrogen? No. What is that? That's an atom of hydrogen. So if I ask for a molecule of hydrogen, what is a molecule of hydrogen? Why is it H2? hydrogen is naturally found as H2. So when I ask for a molecule of hydrogen, I know I'm referencing H2. And I know it's H2 for a couple reasons. One, you said the word molecule, and molecule means more than one atom. So it has to be implied that it's H2. On top of which, even if I just ask for hydrogen, I'm going to be writing H2. Why? That's how it's found. What do you mean that's how it's found? Hydrogen is a diatomic molecule. It is required to be written as H2 because that is how hydrogen is naturally found. Okay? We're required to know that. The have of have no fear of ice cold beer. Okay? If you remember that all the way back to our diatomics. Okay? So you're now saying that's a molecule and not a compound?
Well, I think that would.
What is a compound? Multiple elements. What's a molecule? All right, and I would actually back away from your statement on compounds being multiple elements. Compound is multiple atoms. What was a molecule? Multiple atoms. They mean the exact same thing. Why would you use molecule and not compound? I am very hard put to come up with an explanation for that.
Wait, so if you were to have like sodium chloride, would that be considered a molecule then? So
It is both a compound and a molecule.
okay.
Yeah. Where it could become a little bit gray areas when we're talking about ionic versus covalent compounds. There it is. I already switched it to compounds. And I think that nuance isn't important to evaluate. So compounds and molecules could be used interchangeably, okay, at least for this class. Why is the word compound more useful than molecule? If we were to write out our conversion, 1 mole, 6.022 times 10 to the 23rd, okay, what is the thing that I want to measure? Do I want to pick mole or compounds or molecules? If it makes you feel better, it doesn't matter. Compounds. Ooh, that was a lot of words, a lot of letters. I wish I had a shorthand for that. Cool, I'll accept that, COM. What if I had said, oh God, so many letters. Oh. The rhetorical choice of calling it a compound is actually better because my abbreviation, my shorthand, very clearly differentiates it from a mole. Okay? That is going to be exceptionally difficult for me to do because I'm locked in historically to molecules instead of compounds. So I will try my best to switch to compounds because I think that's a pretty awesome rhetorical choice. So thank you.
You helped him
Okay.
discover new knowledge. This is
That
amazing.
said,
I'm excited. This is student has become the future.
that said, that is going to be exceptionally difficult for me to do, and I will almost always reference it as molecule, particularly if I'm trying to solve a question really, really fast. You will see me reference it as molecule. But I know that that's going to be confusing to use MOL for molecule because it is not the same thing as a mole. So what would I potentially have switched that to? MLC, MLC. Effectively dropping out the vowels that would have made it confusing with moles. What's that?
Hebrew language doesn't have mine.
Okay.
Could you also change the mole to add the E, like how the E is in the parenthesis up there? Could you write one MOLE?
So we could write MOLE for moles.
And
Right,
then
remember-
MOL?
4 letters, 3 letters. Sweet mother, my arm is way too tired. I'm not writing 4 letters. Okay? And for those being, you are such a lazy, yes. Fully accept it. The standard is not to write MOL. The standard is MOLE. E. I don't care. I'm lazy. I'm writing MOL. No one has ever complained about it, okay, from the chemistry outside world, so I'm sticking with MOL. Okay? The moment someone starts complaining, I'll get in a fight with them over it. It's probably a fight I'll lose because the standard is MOLE. That's why I put an E in parentheses, because I don't show the E. Okay? Most people do show it. Okay? It doesn't clarify against molecules, because if we did molecules, MOL, still the E. Okay? So it still doesn't clarify away. This is why compounds is a much better choice. Okay? Make sense? Okay. So moles represent things, not measurements. Okay. That said, I will also refer to the mole as a measurement unit. Okay. What is the measurement unit that I'm calling a mole? Well, it's not mass. It's not length. It's not volume. It's not time. An amount. Okay, it's my measurement unit of an amount. I tend to reference it as the accounting, okay, or literally the word counting unit. It is the counting measurement. 1, 2, 3, 4, 5, 6. So if you hear me ask, what is the measurement unit associated with, okay, moles, what I'm referencing is counting. Okay, so it is a new category of measurement. It's not really a measurement. All we're doing is counting. Yes?
Will that be an exam question?
In that phrasing, no. Because that's not a standard. That's a clarification so that we understand what's going on with it to help with our class and moving forward. Ideally, when you move into 151 or future chemistries, you don't have to reference it as a counting unit. If you've got that internalized, you're 4 steps ahead of the next person that didn't have that separate clarification. Okay? So how do we use this new conversion factor? Because, a new conversion factor must mean we come up with a new method for how we solve things. Nope. Exact same. Nothing changes. So let's go through and look at that question together. What are we solving for? What are we solving for?
Oxygen atoms.
Oxygen atoms. Okay? The default would be to write. I would reference atoms is kind of our counting unit. It's the object that we're counting. What is the symbol for oxygen atoms? Okay. So OA, I understand where you're going with that because we've done that before, but now let's pick kind of a standard system. Oxygen atoms. Okay, I've heard O and I heard O2. What is O2? A molecule. Check ourselves. Do we really want to use molecules anymore? No, we wanted to use compound. So O2 is a compound. Is a compound an atom? No, it's a collection of atoms. How do I know I should be writing O2 or H2 and not O and H? Okay, we could be talking about a compound. The default is we're talking about a compound. How do I know I'm not in the default setting? Because it literally says atoms. Which means our symbol is O. Okay? This is where our solves can become tricky. Remember up on the board we said, why do we choose the thing that we choose to start with? Okay? When we read this question, how many pieces of information are given to us explicitly? What are the 2 pieces? I'm okay with that. Cool. I will absolutely accept that, except that when you see this question on the test, what happens? The top one goes away because you're required to memorize that, which would mean you only have 1 piece of given information. We're going to double back to yours because I like that. Right? Is moles the same thing as atoms? No. So our measurement unit changed. We went from moles to atoms. Okay, our counting measurement changed. What happened to the substance?
Changed.
Also changed. We're going to have to account for both of those conversions when we go through and solve this, because we have 2 things happening. We're changing the measurement and we're changing the substance. Okay? So we have to be very careful to separate those out as two different aspects. Okay? Is it possible to combine them? Absolutely. And at the same time, when you combine them, you likely screw it up. Okay? So let's just avoid that and keep them separate. Okay? Back to Krista's point, at least on this slide, that information was given to us. So let's work with it. Okay? Because that is up there. Okay? I do want to make a modification here. Okay? Am I talking about just atoms?
No, you're talking about atoms of oxygen.
Atoms of oxygen. So while the conversion given to me is telling me what the number means, it's not telling me anything about the substance. Why? That conversion factor only converts the measurement, not the substance. So what I can do is now modify that conversion factor to include the substance. 1 mole of,
Oxygen.
what's our symbol?
O.
O equals
6.0.
atoms of oxygen. Beautiful. Okay, so now you have two pieces of given information. We actually modified one to fit our particular problem better. Which of those two pieces of information do you want to use? We can call it top and bottom.
What are you asking to go next to the equals?
I'm asking you for the next step.
Wouldn't you do the 6.022?
Okay, so you're saying you want to use the top piece of given information.
Yeah.
Okay, I'm cool with that. Why are you picking the top? And it's not because it says 6.022.
Because it's the atom of oxygen.
Because it says atoms of oxygen. Where does the atoms of oxygen need to show up in my conversion? In the top. Why? Atoms of oxygen shows up on top here. Okay? And I forget, did we say we were okay going right to left in our solves?
Yeah.
Yeah? What?
I said I.
Did we get anybody saying no? Okay. What are we relating those atoms of oxygen to? In that top piece of information, it's not just atoms of oxygen. It's also moles of oxygen. So what needs to show up in the numerator, or the other one, denominator? I don't care about the number. Moles of oxygen. Do I have a conversion factor that relates those two pieces? Yes, that is that given piece of information. So now I can bring in those numbers. And as you said, the one goes where? I'm going to say no, and I also heard bottom over here. So those at home, I heard denominator and bottom, and I'm going to complain about both of those. And
It goes with the unit of measurement, the mole.
it goes with moles. Okay? Yes, the moles is on the bottom. That's irrelevant because the moles could have been on top. So don't start placing things on top and bottom. Place them with the unit they were tied to. Okay? We talked about that before. It's a subtle change, but it's a big deal in my opinion. The 6.022 times 10 to the 23rd goes with the atoms. So cool, we brought in atoms of oxygen. We also brought in moles of oxygen. Do I want moles of oxygen? What has to happen? Right? It's going to have to get canceled out. I'm going to have to put moles of oxygen here. Am I given moles of oxygen? Ish. What do you mean ish? It's moles of O2, not moles of oxygen. Everybody catch that? Right? So I can't put this number in there because it's representing the wrong substance. Right? Can I relate the moles of oxygen to the moles of O2? Good. Yes, I absolutely can. What am I changing? What am I relating here? What's the thing that's different, top and bottom?
You have 2 oxygens from the bottom.
2 oxygens at the bottom, 1 oxygen. Yeah. What is that thing? Is it a measurement? Is it a measurement? No, what is it? Substance. I'm converting the substance. Where do I find information about converting a substance? Okay, look at the periodic table. Where does it say ruthenium equals any other element? Okay, that's a bit unfair. Where does it say Ru equals any other element?
I am equal to every other element.
It doesn't. So, periodic table is a useful thing? Not yet. Where do I find the information to convert a substance? Yes. Has it been given to you?
No.
Yes.
Yes.
What? There is no way anything up there relates oxygen to oxygen. Are there 2 oxygen atoms in one oxygen molecule? Remember that stupid formula thing that we walked in? You're like, I don't really know that. Literally right there. And what'd you guys all do? Oh, that's totally not there.
I don't see it.
Okay? What does shift on you here is that we're using the word mole. Do I care? Is mole a counting unit?
Yes.
Yes. Is atoms a counting unit?
Yes.
Yes. Okay? Is the measurement unit changing?
No.
So, as long as we're in a counting unit, guess what we can do? We can drop those numbers straight into our thing. How many moles of oxygen?
2.
Why do I say 2? There are 2 oxygens in how many oxygen molecules?
1.
Well, that was it. That's all I had to. Yeah!
Yay, we're smart.
Where did you get the...
The oxygen. Where is the 2 coming from? So you just literally moved it.
Not quite that I literally just moved it. I'm interpreting the knowledge there.
Yeah.
That oxygen molecule literally says that there are 2 oxygens in one of those things.
Right.
All I'm now doing is taking that numerical information out of the formula and putting it into a place where I can use it mathematically.
Okay.
Right?
Are you having a hard time going from how did he get from a fraction to an equal sign? Is that what you mean?
No.
Right there? No, you get that? You remember him
No.
doing that?
No.
Okay?
'Cause
And
yes,
believe it or
that's
not,
an important thing.
this step is one of those big steps that a lot of people just miss. Okay? And I don't want to make it sound like I'm insulting for this, but I think that step is so easy
Right.
that you're like, that can't possibly be right. But it is.
Yeah, I feel that
Okay.
way. Because like yesterday, with the one that you, or Tuesday, I was like,
It
wait,
needs to be something more.
yeah.
Okay? Well, so something more. Have I solved the question yet? No. How do I know that?
You need to do the.
Moles of oxygen cancel. Now I have
2 moles of oxygen.
I have moles of oxygen molecules here that I don't want in my answer. So what has to happen?
Gotta get rid of it.
I got to get rid of it. So moles of O2 would need to show up in the numerator so that unit cancels. Am I given moles of O2?
Yeah.
Sweet hallelujah. What can I do?
Put it in the numerator. Put it next to the.
Put in a numerator. What goes in the denominator?
1.
1. Now what happens? Punch it into the calculator. My units cancel out. Ta-da! There's my answer. Okay?
What do you put in the calculator though?
What would you enter into the calculator? This one is a more straightforward one to enter into the calculator. So my recommendation in general, and if you go back to that big long paragraph thing, the very bottom of it explains what to enter into the calculator. Take everything in the numerator, multiply it out. Everything in the denominator, multiply it out.
But I'd do the .240 and then I.
Where's the .240 located? In the numerator.
But for the mole.
Do I enter moles into the calculator?
No, the calculators can't do that.
The calculator doesn't deal with the text. The calculator only deals with the number. Okay, that's it. So you're using the text to tell you what to enter into the calculator. If you start punching numbers into the calculator, you don't know why you should enter them there. The calculator's not going to do it wrong. It's going to do the exact calculation you told it to do. Okay? But if you aren't telling it where to place those numbers correctly, it's going to spit out a number that's going to be wrong. It will also spit out a number that is one of your multiple choice answers. Okay. What's that? No, it doesn't. Yeah. So that's the measurement substance. That's our measurement and substance. Just like grams. There isn't a gram button. Okay?
When you enter it into the calculator for the 6.022 times 10 to the 23rd, do you have to do that in parentheses so that way
So,
the calculator knows only...
In general, with these complex powers of 10s things, it's usually a good idea to put them in parentheses. In this case, it's not going to matter because everything is in the numerator. But if that 6.022 times 10 to the 23rd got dropped into the denominator, if you don't put it in parentheses, your power of 10, all of a sudden, your calculator thinks you want to multiply it and puts it in the numerator. Okay? So this is where entering things into the calculator becomes important, and you have to be very careful with where you align that.
Okay, so if it's in numerator, then you don't have to parentheses.
You don't necessarily have to put the parentheses. As a general habit, it's usually a good idea. Yes, Zeke?
You wouldn't care about the sig figs here, but as well.
Yeah, theoretically. Okay? And I would say theoretically, because on a test, this is probably going to show up as a multiple choice. And in the multiple choice, do I really want to waste a bunch of answer choices on sig fig rounding? Probably not. Probably what I'm testing for is, did you memorize Avogadro's number? Okay? And then do you know how to interpret Avogadro's number correctly? Do you know how to interpret the chemical formula? Can you put it all together? Okay? So on a test, I'm probably not going to throw a multiple choice answer up there that's a sig fig rounding thing because there's too many other things that I'm testing for. It's not worth my time.
And one of the big things I've seen come up in the past is the ability to draw from like the chemical formula that conversion factor.
Yeah, that conversion factor. So, and we are kind of out of time, but it's okay. One of the complaints that I have heard, and it wasn't from your class, it was from the standalone, okay, was, dude, he's spending all this time on stupid mathematics and no chemistry. The only thing that I would argue is chemistry here is this conversion factor. You mean that thing that you were like, isn't that too easy? Chemistry is freaking easy. All it is that conversion factor. That 2 moles equals 1 mole of O2. That's the conversion factor. That's chemistry. The rest of this? Mathematics. Don't blame me for you not liking mathematics. Sorry, Pam. Okay? All I'm telling you to do is to use that information correctly to interpret through. Okay? We will pick up there on Monday. We're going to have to pick up some speed on this because we need to get through this. So what's going to end up happening is we're going to see just question after question after question that's practice on running these conversions. I'm going to start shrinking the time that we spend on each of those conversions because we need to start getting through these to some more advanced aspects. Okay? So good job today. I like the questions. Hopefully I remember the compounds thing. That was a good one.
If anyone was trying to figure out